Alrighty. So, the quiz from Friday is graded and put in, and honestly, it was pretty good. It was not too shabby. The class average was a 71%. Okay, so that's a C. So that is not bad. Naturally, there were some high, there were some low, but the average was a C. All right, that's definitely something we can work with. If yours was lower than you'd like, we can look towards thinking about a corrections if you want to, just to kind of get this semester started off where we want it to be. The corrections or the test retake policy is that you have to have all of the homework in, including the reviews. Luckily, we now have those online versions of the homework where you can do that easy peasy at home. But, yeah, then you have to come in and do corrections, and then we can schedule a retake. But a lot of it's done outside of class time or during work time, stuff like that. Okay, but all in all, generally, I thought it was not too bad of a quiz. We did all right. Okay, the reason this chapter is divided up into two quizzes like this is because there are the concept we started with, which was our inverses, and then it feels like it moves into an entirely different piece here because we're going to start working with square roots a lot. So instead of having that be one monster test that does everything from inverses to square roots, we cut it into two pieces. So we're going to focus a lot on square roots, which means what we need to do is remember as many square roots as we can, and that's what this bell work is. We are asked here to list out as many perfect squares as we can. So what are some perfect squares that we know? What are perfect squares? Where you can square root a number and you get a whole number. So perfect square, like 1 squared is 1. 2 squared, 4. So 1 and 4 are both perfect squares. 3 squared, 9. 4 squared, 16. 5 squared, 25. 6 squared, 36. 7 squared, 49. 8 squared, 64. 9 squared, 81. 10 squared, 100. There we go. I'm sorry, I'm writing different numbers than I'm saying. So we do 10 squared as 100. Do we know 11 squared? Say it again. 121. How about 12? 144. We don't often ask you to go higher than that, at least not as a quick reference. If you care, 13 squared is 169. That's about as high as I go, even with my mental math, is 169. Most of the time, we're going to be able to use calculators for these kinds of things. But having these be something we can recognize off the bat will be helpful when we're starting to try and spot patterns. Then we're going to do the same thing, but instead of perfect squares, so these are numbers that we squared, we're going to look at perfect cubes, because we're going to deal with all kinds of different roots here. So what about 1 cubed? 1. What's 2 cubed? 8. 3 cubed? 27. Yep. 4 cubed is 64. 5 cubed? 125. And that's usually about as high as we go in cubes as well, right off the bat. And again, these are not things that are critical to memorize. Like, we don't need to be making flashcards. But being able to spot them and go, hey, that looks familiar, maybe that's a something, is ideal. Because we're going to be working with cubes and squares a lot over the next 2 weeks. Month. So So then our last piece is we're going to look and see if we can figure out the square root of 324 without using the calculator. Or at least not using it too much. Great. It's like there's a lot of ways you can do this. We can use our calculators. If we know it, great. You can birthday cake. If we remember that one from like middle school where we take out prime numbers. 324 is even. And it would give us 162. No, 172. No, I don't know. Grab a calculator. 324 divided by 162. Somebody do it because my mental math is not great right now. Oh, 324 divided by 1. But 324 divided by 2? Or 324 divided by 162. That's totally fine. It gives me the same answer. It means I did my math right. Woo! That means this is still even. So if you remember like this thing, where again we can take out a 2. Notice that this is 81. 81's a perfect square, so we know we can take out a 9 and a 9. So if you remember your birthday cake, it'll look like this. You can also do prime factorization. You could notice that this is in fact divisible by 4. And do this as square root of 4 times 81 to get the square root, or to get 2 times 9 to get 18. This one is where we're pulling out pairs. We get a 9. We get a 2. And there's a lot of different techniques for finding our square root. Either way, we wind up at 18. Make sure you know one of the ways to do it that's not just type it in the calculator, because when we start tossing in variables, it becomes things we can't just toss in a calculator. I don't care how you do your square roots. If you like to do a factorization under the square root, if you like to do a birthday cake, which is a method of prime factorization, if you like to just straight up do a factor tree, if you like to find your perfect squares under the radical, I don't care how you do it. I do not care. There are a gazillion different ways to factor a radical. More often than not, I'm going to use this way where I split it up into perfect squares, or as close to perfect squares as I can, because this takes up physically less space on the screen and I can write it at a decent size. This takes up so much space. So I tend to do it this way under the radical, but it gives us the exact same answers as these kinds of things. Okay? Because we're going to start working in radicals and with all kinds of different radicals. And I'm going to put up a giant wall of text. You do not need to copy the whole darn thing down. Again, this is stuff in the text. The piece on this that you need most is this picture. There's a whole lot of words up here, but you need the picture with all the labels on it. In fact, I'm going to just change the screen so you can see that, because I know it's written in very light colors. You need this information. We're going to be dealing with radicals, and we are sometimes going to be dealing with funky radicals. They're going to have different indexes, and I'll talk about what that means in a second, but I want you to write this information down. Including that n is our index. Under the radical symbol is our radicand. Sorry, my screen's being a jerk. All right. So the index is the number that's in the little hook. It's this guy here. So when we're working with square roots, there's a little... Hello.
Pardon this interruption. WEDA's testing starts today. Students in Group F are testing during periods 1 through 4 this morning and should make their way to X214 upstairs to the Freshman Center. Group F students and teachers received an email this morning reminding them who is testing and where. Thank you.
Genuinely, I did not open my email yet this morning. We love that for me. All right, so in our square roots, there's an invisible index here. We don't usually write it because it's assumed that there's an index of 2. When we do something like a cube root, there's an index of 3. We can do something like a 4th root, which has an index of 4. All it means is that in our index, we're going to pull out our perfect squares. We're pulling out groups of 2. With our index of 3, we're pulling out groups of 3. We're pulling out perfect cubes. Index of 4, it's perfect quartics or fourths or groups of 4. So we'll work through practicing with those. We're not often going to do tons with higher indexes simply because they're obnoxious. But it's good for us to know what the heck those mean when we get into them. Okay, so our nth root, that's what it means when it says n. That's how we read that, is the nth root or the 3rd root or the 4th root or the 5th root is our index. And it's all about how many pieces we pull out. So we're going to start practicing finding some roots. And we'll get a few kind of funkier ones as we go through. Sweet. Just making sure we did have them. So we're going to start with the square root of 25x to the 4th. And the way I do this, when I have 2 different kinds of terms like this, is in my head, the way I do it is I break these up into pieces. So I'm going to split this up to be, it's going to feel very much like when we did imaginary numbers. If you think back to that, I'm going to do this the same way I did that. I'm going to switch this to be 25 times x to the 4th. So I can make this be square root of 25. Oh, you're right. Thank you. Boop. Oh, it's because my screen's being a jerk. There we go. Got it. Sorry. Thank you. Oop. That one. Okay. Then I'll talk it through again. Boop. I'm just going to redo it. So I'm going to take this to be square root of 25 times x to the 4th, which I can then split apart into be 2 different radicals. Square root of 25 times the square root of x to the 4th. It's easier for me to think about these individually, especially once we start getting a whole bunch of terms on there, or if we have them in weird units. What is the square root of 25? 5. What is the square root of x to the 4th? X to the what? X squared. The way we can think about this is we're going to take whatever our index is, and we take on our letters, we take our variable x to the 4th, oops, and I'm going to divide the power by the index, 4 divided by 2. So our answer is going to be x squared. On a square root, there's always an invisible 2. We just don't usually write it, but it's because it's always squared unless we put something else. So there's always that is not what I meant. I didn't even touch it, y'all. On a square root, there's always an invisible 2 right here in this nook. The index is 2 unless we tell you otherwise. So the square root of 25x to the 4th is 5x squared. Then let's look at this right one. I've got the square root of the quantity x plus 7 squared. And what can we do over here to simplify? What's going on over here that I can simplify? Say it again. I don't want to take them out of the parentheses because what I have here is I've got a square root and something squared. What happens between the square root and the power of 2? They cancel out. Again, because this is an index of 2, we are dividing the power of 2. Whatever your power is, you're dividing by the index. So the square root and the square cancel out, and we're just left with x plus 7. A square and a square root, those are inverse operations, so they undo each other. Questions on these two? Because you'll know it's going to get a little crazier. Okay. Next set. Slightly different. So now I don't just have a square root and a square. I have a square root and a 2 to the 8th. So what we're going to think about is that kind of piece that I was talking about a minute ago, where we're going to take our index, in this case it's a square root, so my index is 2, and whatever my power is here, we're going to divide them. This is going to be 8 divided by 2 for my power. Because it's a square root. The default state is 2. If it doesn't have anything written there, your index is 2. If it is anything other than 2, we will tell you. Okay. So what's inside the parentheses doesn't really matter. I just care about the power right now. So my y cubed minus 3 still hanging out. What is 8 divided by 2? 4. So this simplifies down to be y cubed minus 3 to the 4th power. Whatever our power is, we divide it by the index. Or we figure out how many groups of 2. If you think about it as, you could also do it as the pairs of socks situations. If I have 8 chunks of this and I need pairs, I can make 4 pairs. This works really, really well when they are divisible. Since this is an even number, that makes it very, very easy. The next one is significantly more challenging because we don't have easy peasy even numbers anymore. So our next one is the square root of 12 times x to the 7th times y to the 9th. And our answer is going to have a radical in it still. We're not going to be able to fully simplify this outside the radical. But we can simplify it a bit. So I'm going to split this up like we did on the first one. Since I have 3 different pieces here, I'm going to split this up to be the square root of 12 times the square root of x to the 7th times the square root of y to the 9th. If we do that, it's easier to look at one piece at a time. Because I can come in here and just look at the square root of 12, which I'm going to zoom it in on just the square root of 12 as soon as you guys catch up with where I'm writing. I'll try not to pop ahead of y'all. Okay. I'm not erasing anything. I'm just going to zoom it in. Because then I can just zoom in and look at the square root of 12. And we can simplify the square root of 12. How can I simplify the square root of 12? Is there a perfect square inside 12? What perfect square multiplies against something to make 12? What multiplies to make 12? Yes, because I can write 12 as 4 times 3, right? 4 is a perfect square. We know that. So I can make this the square root of 4 times the square root of 3. What is the square root of 4? 2. Do we know the square root of 3? No. Gross. Decimally grossness. So the square root of 12 simplifies down to be 2 square root of 3. So we're going to wind up with radicals left over. We can do something similar here. I would like to, with my x to the 7th, I want to find a power that's going to square root out of x to the 7th. Well, with square roots, it'll work with evens. So I could make this x to the 6th times x. Because I can do the square root of x to the 6th. We can't do the square root of x. What is the square root of x to the 6th? X to the 3rd. Is this one right here? We're looking at this guy. So this gives us x to the 3rd times the square root of x. I'm looking for things I can use with my index and play around with. So then let's do our y's. Same vibe. I'm still in my square roots, so I want my y to have something even. So I'm going to take y to the 8th times y. Do not like that 8. I'm going to fix it because I hate that. There we go. So I could make this the square root of y to the 8th times the square root of y, which is going to give us what? What is the square root of y to the 8th? Y to the 4th, divide by our index, remember? And we have the square root of y. So these are all of our fully simplified pieces, but it looks like a hot mess now. So what I'm going to do is I'm going to clump together all the things that are outside my radical. So I have 2, and I have x to the 3rd, and I have y to the 4th. And then we have everybody that's inside the radical together. I'm going to have my 3x y. And this, let me grab a, there we go. This is our answer here. Zoom it out so we can see it. So we're splitting things apart and splitting things apart and then continuing to split things apart until there's something I can simplify. So we're breaking them up into pieces. Questions on this one, because this one feels super complicated. Okay. The 3xy, that was all of our guys that were in the radical. So there was the 3 that was in the radical here, and my x that was inside the radical here, and my y that was inside the radical. Because these are all, ooh, that's not what I meant. These are all separate lines. That is not the color I meant. There we go. These are all separate lines, but they're all the same thought. So these, we just did them one at a time vertically. Okay, we're going to try that again. But it's going to get a little more. Somebody's calling me. Pieszki. Mm-hmm. I don't think I have her this period. Oh, no, I do. There she is. Never mind. I see her. Sorry. I was reading the thing wrong. X214. Got it. Mm-hmm. Diana, grab your stuff, please, dear. All right, now we're going to do some very similar things, but this time we have an index of 3. So we're going to be looking for perfect cubes or groups of 3. So the first one says the cube root or the third root of 8. We wrote this at the beginning when we were looking at our roots that we knew. We can write 8 as 2 cubed. 2 cubed equals 8, right? Now I have a cube and a cube root, and they cancel out. So the cube root of 8 is just 2. Because my cube and my cube root cancel out. So it's the same process. We're going to be looking for perfect cubes that we have in here, or groups of 3s. On the middle one, I'm going to split it up into separate pieces. I'm going to make these all be multiplications. So we're going to have the cube root of 125 and the cube root of x cubed and the cube root of y to the 6th. And the cube root of 125 should hopefully be familiar. We again showed that one at the beginning when we were looking at our perfect cubes, because 125 we can also write as 5 cubed, right? 5 times 5 times 5. You can also do it as a prime factorization. That's 5 cubed. I don't like doing that. I like it better that way. Because then we can see how our index and our power simplify out to give us an answer of just 5. That's not what I meant. Then we're going to look at the cube root. That is not what I meant. Laser pointer. Thank you. The cube root of x cubed. And again, we can think of that as taking my power of 3 and dividing it by my index of 3. So x to the 3 over 3, that's just x to the first, or x to the 1, or x. We're looking for groups of 3 we can take out. Well, I only have 3 x's, so I can take out one group. Same thing with the y's. You can either think of it as division, 6 divided by 3, or we can think I have 6 y's, I need to take out a group of 3, and I have 2 groups of 3. Or 6 divided by 3 is 2, and that's my exponent. Questions on that one? Because I feel like the cube stuff tends to throw us off. Yes, dear.
So would you count points off if we just wrote it as x?
Absolutely not. X to the 1 and x are exactly the same thing. It's like just writing your name in lowercase instead of in capital. Same dang thing. Works for me. Okay. Let's look at this funky one with the division. Because this is now expecting us to remember some exponent rules, because we treat radicals like they're exponents. So what we can do when we have something like this is we're going to take, like how we took it and all divided it into separate multiplications, we're going to split this into separate divisions. We're going to do the cube root of 64x to the 5th over the cube root of 27y to the 7th. So when you have one big monster fraction like this, we're going to split it up into pieces. And then we're going to deal with each one individually. We're going to take our numerator and our denominator and simplify each of them. So I'm going to take my numerator, which I'm going to give myself a little bit more space down here. There we go. My cube root of 64x to the 5th. 64. What is the cube root of 64? Yeah, 64 we can write as 4 cubed. So the cube root of 64 is just the 4 part. How about for x to the 5th? Yeah, I can make this be x cubed times x squared. So that's going to let me take out one group. So we're going to have x, but I have a leftover cube root of x squared because I can only take out groups of 3. I cannot take out this group of 2. So my numerator, which I am vastly running out of space. We're going to go to the right. My numerator simplifies down to be 4x cube root of x squared. Then let's do our denominator. Same vibe. We're going to take our cube root of 27 and the cube root of y to the 7th. So what is the cube root of 27? 3. And how about for y to the 7th? How many groups of 3 can we take out? 2. So I could write this as y to the 6th times y, if that helps you that way. And notice that we get y squared outside, and we have a leftover y who's got to stay inside. And that is a hot mess of writing down there. So we have our 3y squared cube root of y. And it's a mess. And it's a thing. And it's gross, but that's what our answer is. I'll highlight it so we can see it. This is going to be our answer. If you look online or answer keys and stuff, they're never going to leave a radical in the denominator, but we're not going to worry about dealing with that. I'm 100% okay with us leaving radicals in the denominator. Just know if you look online, it'll give you like another weird step after that to fix that. But honestly, I don't care if we rationalize. Okay. We only have a couple more minutes until the announcements, so I'm going to pass out the homework. Okay, it's dealing with these radicals and square roots and all these kinds of dealios. So you can do the top half of the front, and honestly, you can probably do about half the back too. But the bottom half of the front is what we're going to talk about tomorrow. You might be able to figure it out because I kind of teased on it today. Used it a little bit, but I'll give you details about it tomorrow. Alrighty, so our next quiz, the second quiz of this chapter is going to be on the 2nd. We've got a couple weeks. Actually, that's a week from Friday. Gosh, that's crazy.